Hello students, myself Dr. Divya, Assistant Professor, Department of Chemistry, Institute of Aeronautical Engineering. So in this session, we will understand and learn the fuels, its definitions and classification of fuels. So here are the topics. First of all, we have to understand what are the fuels, its definitions, then classification of fuels, then characteristics of a good fuel. How does a fuel becomes good because of its characteristics? Then calorific value, how the fuel's calorific value is expressed. Then its measurement using bomb calorimeter. Then solid fuels. In solid fuels, its example is a coal and its types. So let us understand what are fuels. Fuel is something which burn to give heat in the presence of oxygen. So it requires oxygen, so it burns and gives heat. So this heat is used in our daily life. Like for example, cooking, we are using fuel, LPG gas as a fuel for burning and getting heat used for cooking. So some of these are the examples of fuels. So what is the fuel here? Wood. Wood is a fuel here, and this is the CNG gas that is used for automobiles, and also the coal and then petroleum. These are some fuels examples of fuels. So if we see, how does the burning takes place? It is the chemical reaction that is occurring. It is the combustion reaction. So it is a process of burning a fuel. So combustion takes place. So what happens in this combustion? The hydrogen and oxygen reacts, forming water molecule, or the carbon and oxygen forms carbon dioxide. So as we know, fuels contains large amount of carbon. Large amount of carbon. So this carbon on heating, so while burning, it combines with oxygen. So that will give carbon dioxide. Whatever the gas that is coming from this combustion reaction is carbon dioxide. The other one is the methane. In the presence of oxygen forms carbon dioxide and water molecule. So these are some of the combustion reactions that will take place. So the most of the fuels contains highest amount of carbon in it. So in the fuel, when combining with oxygen, gives a heat and exhaust. So this heat is used for domestic and industrial purpose. Domestic and industrial usage. So the combustible material which on proper burning gives large amount of heat which can be used economically for domestic and industrial purpose. So domestic, for example, we take like cooking, boiling, so on. Industrial purpose for industries, burning of or synthesis techniques, wherein we use Bunsen burner or some other fuels in the industry usage. So what is the classification? So if you see the classification, there are two different types of classification. Two types of classifications. How? It is like based on the source. So based on the source, from where it is coming from where the fuel is coming from. So based on the source, it is natural or primary, and next one is the synthetic or secondary. Natural is occurring in nature or the earth, that is available readily. Synthetic are obtained from the natural, that is nothing but the secondary fuel. So based on the physical state, so we know there are three forms of matter. So based on the physical state of that particular fuel, like solid or liquid or gaseous state of fuel, it is differentiated into three types of fuels: solid fuels, liquid fuels and gaseous fuels. So what are solid fuels? Solid fuels are, for example, wood, coal or charcoal. This comes under examples for the solid fuels. Solid fuels, the matter or the state of matter of that particular fuel is in solid state. So if we see this, they have the compact solid state, wood and charcoal or coal. So they are the good examples for solid fuels. The liquid fuels are like kerosene that we use for our lightening lamps and petrol or diesel for automobiles. So we use for automobiles petrol or diesel in liquid form. So these liquid fuels are used in automobiles. Kerosene example is used for lamps. So this is some of the examples for the liquid fuels. Then gaseous fuels are like CNG, LPG gas, biogas or hydrogen gas. So for example, we are mostly now seeing the CNG automobiles or three-wheelers having CNG gas that is used for automobiles, auto rickshaws. So that is an example for its application. And also LPG gas used for the cooking is also a good example that we use in our daily life domestically. And what are the characteristic properties of solid, liquid and gaseous fuels? So there are some of the properties of solid and liquid gaseous fuels. So for example, examples for solids are coal for solid fuels, liquid fuels, crude oil, gaseous fuels, coal gas. And in the aspect of cost, it is cheaper. Solid fuels are cheaper, liquid fuels are costlier than solid fuels, gaseous fuels are more costly. Then storage, if we see the property of storage, easy to store, solid fuels can be easily stored. So there is no question of leakage because they are compact in nature, so therefore they can be easily stored. Liquid fuels should be closed in a closed container, should be used for storing. So it should be used for storing wherein the containers are closed. Then gaseous fuels, storage space required is huge and should be leak proof. This is very important because if we are storing the gaseous fuels, it should be leak proof because we cannot see the gas that is leaking out of the container. So that is how we use the LPG gas with other additives so that it smells. Whenever there is a leakage, it smells. That is why we use additive for indicating that there is a leakage. So it should be always preferred to have a leakage proof container for storing gaseous fuels. Then risk towards fire hazards. How much is the risk for fire? So flammability, it is less for solid fuels, more for liquid and very high for gaseous fuels because the combustion is high for liquid and gaseous fuels. So the risk for the fire hazards is more for liquid and gaseous fuels. Then combustion rate, it is a slow process for the solid because it has an atomic structure of compact atomic structure. The solid fuels takes time for the combustion reaction, whereas it is free in state for the liquid and gaseous fuels. So it is faster for the liquid and gaseous fuels and therefore they have high combustion rate. Combustion control, if we take the property of combustion control, cannot be controlled for the solid fuels and for liquid cannot be controlled or stopped when necessary. But for the gaseous fuels, controlled by regulating the supply of air. So if there is the regulation for the supply of air, the air supply is regulated, then gaseous fuels combustion rate or the control can be done for the gaseous fuels. The next is the handling cost. So based on the cost, it is high for solid fuels since laborious required in their storage on transport because they are huge. They have bigger in size, so they require storage and transport requires laborious jobs. So that is why the cost is high for handling. Low since for liquid it is low since the fuel can be transported through pipes or pipelines. So it is less for the liquid fuels and it is also low for gaseous fuels similar to liquids. This can be transported by pipes. So we have seen some of the areas in India also there are LPG pipeline for the houses. So that means pipeline for household purposes. That means we are using pipeline for the storage and transport. There is no need for the transport, expensive transport methods used for the gaseous fuels. So therefore the handling cost will be lower. Then ash. So what is the ash that is produced? Ash is produced and its disposal also poses problems to the environment. So when burning solid fuels like wood or charcoal or coal, there is ash that is producing out of this reaction, which requires again regeneration of this or proper disposal of this ash to avoid any problems to the environment. Then in the liquid fuels, no problem of ash. So liquid fuels will not produce ash, and in the solid gaseous fuels also no ash is produced. So for example, if we see our normal stove that we use for the cooking, there is no ash produced. But when we use the traditional cooking method with 3 stone or some other method, we required that we see that there is ash production that is to be again disposed properly. So that is the main, we can just compare and remember that no ash problem in liquid and gaseous fuels. However, ash is produced in large quantities for the solid fuels, which needs proper disposal. Then smoke. Smoke is also produced in the solid fuels. So produce smokes in the solid fuels, whereas in liquid clean but liquids associated with high carbon and aromatic fluids fuels. Aromatic fuels with high carbon content produce smokes. But however, when the gaseous fuels, no smoke is produced. No smoke is produced. Calorific value, it is least for the solid fuels, high for liquid fuels, and the highest for the gaseous fuels. And heat efficiency, it means the heat produced is less in solid fuels, high for the liquids, and highest efficiency for the gaseous fuels. So this is the handling cost that we have already discussed. So these are the different characteristic properties of that particular 3 different types of fuels that are there. So if you see when does it becomes a good fuel, the fuel should be easily available. It should be easily available. Then it should be dry and should not have no or less moisture content. So what happens when there is a moisture content? The heating will take place longer. So should not have a moisture content. So dry fuel increases calorific value. It should be cheap, easily transportable, and have high calorific value. So the fuel whichever is present should be cheap in cost, should be easily transportable, and have high calorific value. Then it must have moderate ignition temperature. It means the ignition time and temperature should be moderate and should leave less ash. The ash should be less after combustion. So the moderate temperature and less ash is also a requirement for becoming a good fuel. The combustion speed of a good fuel should be moderate. So the speed of this combustion reaction that is taking place should be also moderate, not very less and not very fast. So it should be moderate in nature so that the combustion is better. And it should not burn spontaneously. So if it is burning spontaneously, what happens? It will catch fire. It will catch fire vigorously and cause fire hazards. So in order to avoid these fire hazards or fire accidents, it should not burn spontaneously. Its handling should be easy and should not give poisonous gases after combustion. So any fuel should be good for the environment. Ultimately, the environment has to be protected. So it should not produce any poisonous gases after combustion or during its usage. So the combustion of good fuel should not be explosive. Explosive is like, again, it is giving rise to flammability. So it will lead to fire accidents. So the combustion of any particular fuel should not be explosive in nature. Then comes the calorific value. So this defines the nature of any fuel. So it will help in understanding what is the capacity of that fuel during its usage, so that we can select particular fuel for any application. So the total amount of heat liberated when unit mass or unit volume of a fuel is burnt completely. So it is the total mass, a total amount of heat that is generated or liberated when one unit of or one volume of fuel is burnt completely. So the combustion takes place completely, so that there is some heat evolved or liberated. So that is nothing but it gives the calorific value of particular fuel. So it is given in two ways. It is gross higher calorific value, gross or higher calorific value, designated as GCV or HCV. The net or low calorific value. Net or low calorific value. So this will help in understanding the capacity of that particular fuel during its application. So we will see in detail how a high calorific value will give us an understanding. So this high calorific value is defined as the amount of heat obtained on complete combustion of unit mass or liquid or unit volume of gaseous fuel at standard temperature and pressure. STP is standard temperature and pressure conditions. So we are burning a fuel, standard temperature and pressure. So we are burning a fuel completely at these conditions, and the products of combustion must be cooled to room temperature. So the products that are obtained should be cooled to room temperature. So that will give the higher calorific value. So we are obtaining the maximum heat that is evolved. So that will give us the higher calorific value. The net or lower calorific value, it is defined as the amount of heat obtained practically on complete combustion of unit mass of solid or liquid or unit volume of gaseous fuel at STP, and the products of combustion are allowed to escape. So the product can be escaped. So generally in some cases what happens during combustion, the product escapes or the byproducts escape with some heat. So the amount of heat that is evolved or used in particular application that is practically applied is nothing but the net calorific value or low calorific value. So the relation between the gross calorific value and net calorific value can be given like GCV or gross calorific value is equal to net calorific value plus 9 multiplied by H into latent heat of water divided by 100, or GCV is equal to net calorific value plus 0.09 into H into 587 calories per gram. So this is how there is a relation that is relating between the gross and net calorific value. So this will give an understanding and how this can be used in practical applications, like we will be selecting depending on if we require like high calorific value fuel, we will select depending on the values we obtain for the calorific value. So calorimeter is used generally to understand, to get the values of this calorific value. So what is the principle lying behind? The total heat liberated by complete combustion of a known amount of fuel is absorbed by water or the known mass of water present in calorimeter. So calorimeter has some water inside. So whenever there is a liberation of heat due to combustion of that particular fuel, this water will absorb that heat. So it is directly proportional to the absorption of heat that is done by the water with the evolution of heat. Heat liberated from fuel is directly proportional to the heat absorbed by the water, So that is a simple technique we are using in determining the calorific value. So from the rise of temperature of water, the calorific value of the fuel can be calculated. So this increase in the temperature of water gives an indication of calorific value of that particular fuel. So bomb calorimeter is used for generally for solids and liquids. Solids and liquid fuels. Liquid fuels. So a known amount of solid or liquid fuel. So if this is the bomb calorimeter, so we are taking a known amount of solid or liquid fuel in the excess of oxygen. So we are pumping oxygen also in a closed pot, and the products of combustion are cooled to give gross calorific value. Gross calorific value. We are cooling calorific value. So the products that are obtained from this reaction are cooled to get maximum heat that is obtained, that is nothing but the gross calorific value or high calorific value. High calorific value. So this consists of a bomb pot. There is a pot here. This is the bomb pot. This is the bomb pot. It is made up of stainless steel. It is cylindrical, strong stainless steel pot with lid fitted airtight to bomb pot. So this is fitted airtightly to the bomb pot. This is the lid. This is the lid. There is a provision for the oxygen inlet also. So two electrodes fitted to the lid and oxygen inlet valve at the center. So these are the two wires, electrodes that are present, and the oxygen inlet. From this oxygen is sent. So one electrode provided with ring to hold crucible. So this one of the electrode is provided with a ring so that it is holding the crucible containing sample. Crucible containing sample or the fuel. And resistance wire in loop form touches the fuel. So there is a resistant wire. There is a wire, if you see here, there is a loop wire that is present here that touches the fuel or the sample present in that particular crucible. So calorimeter, it is made up of a steel or copper in which this bomb pot is kept. So this is the calorimeter. On a whole, it is called calorimeter. So this is covering the bomb pot. So this is the bomb pot. It is embedded in the calorimeter. A known volume of water is added so that bomb pot is completely deep. So if we see the level of water is above this bomb pot, it means the calorimeter is having water that is containing, that it contains water, so that the bomb pot is submerged in the water. So it means whatever the heat that is evolved from this reaction will be absorbed by the water. So how does we indicate that? Like from the Beckman thermometer, we are using a thermometer. Here is a thermometer. So that is Beckman thermometer is used to measure temperature of water in calorimeter and stirrer for stirring water. So why are we using stirrer? For uniform distribution of heat, so that even the thermometer here or here or here, the temperature should be similar. So we are using stirring that is the use of stirring. So whenever the thermometer is touching the water, there should be the rise in temperature of water due to combustion reaction that is taking place in the bomb pot. And the water and the air jacket is also present. So the whole calorimeter is again secured with a jacket of water. So this is the water jacket that is present. So that will secure so that the heat is not coming out from the apparatus. So it is also, that is nothing but to avoid the heat loss due to radiation. Then what are the other accessories that we use? Pellet press to form pellet of fuel. So if we are using any liquid fuel, so it will be solid or liquid fuels, a pellet press is used so that it will form a pellet, and that can be used in the crucible. Oxygen cylinder to supply oxygen to the bomb pot at a pressure of 25 kg per centimeter square, and DC battery with 6 volts to start combustion of fuel. So it will supply voltage to this sample through the electrodes that are present, so that the combustion will start. Then working, if we see, weigh pellet of solid fuel, add 10 ml of water in the bomb, then fill with oxygen, place bomb in calorimeter, add known volume of water, place calorimeter in water jacket with Beckman thermometer and stirrer, make electrical connections and pass current from a battery for 5 to 6 seconds. Wire burns and fuels also, and note the temperature reached and average fall of the temperature per minute. It means the sample, this is the crucible, stainless steel crucible that is present. So we will take solid or liquid fuel, solid or liquid fuel. So this solid or liquid fuel, when we add some 10 ml of water, it will stick to the crucible. Then we apply voltage from the electrodes, so that is connected to a battery. So once we supply energy, there is reaction that is going on. What happens? This wire will burn and the sample will be burning. So combustion reaction will take place, and there is a evolution of this combustion reaction. The energy or the heat will be evolved to the water present in outside this bomb pot. So then happens then we use the temperature thermometer. This thermometer will read temperature. So this will read temperature. So there is a rise in temperature. Why there is a rise in temperature? Because there is a formation of combustion reaction. So when combustion is taking place, heat is liberated. So when heat is liberated, upon stirring, it distributes equally, and there is rise in temperature. And there is also fall of temperature, because once the reaction is completed, the temperature will come down. So here are the calculation that we use. Let the mass of the fuel be x grams. Mass of water in calorimeter is W grams. Then water equivalent of calorimeter set is W small w. Then gross calorific value of the fuel is L calories per gram. So rise in temperature of water is nothing but T2 minus T1. So T1 is the initial temperature of water. Then T2 is the rise temperature of water. So obviously the rise temperature is higher. So T2 minus T1 will give the rise in temperature. The temperature after combustion reaction. So that will after combustion temperature, or the combustion reaction, after combustion reaction. So that will give us the temperature, rise in temperature of water. So heat liberated by burning fuel is equal to heat absorbed by water and calorimeter. So this is how we use the temperature that is varying from initial to after combustion reaction to get the gross calorific value. Then the other one is the Boyle's gas calorimeter. So it is known to burn. Gas burner is used. So here it is used to burn the gas. Then combustion chamber around the burner with copper tubing, inner and outside. Water enters from top outer coil and moves to the bottom of the chimney, then goes up through the inner coil. So what happens? This is especially used for gaseous fuels. Gaseous fuels. So in the previous one, bomb calorimeter, only solids and liquids can be used for determining the calorific value. But what happens for the gaseous fuels? Boyle's gas calorimeter is used. So in this, what happens? The burner, whatever is present here, is used for combustion reaction, to initiate the combustion reaction. So this is the chimney that is there. So there is water inlet water is going into the chimney. So there is a combustion reaction that is taking place, and also the heated water will go into the from the inner coil. From the inner coil, it will go into the other side. So through this way there is again temperature reading thermometer present. So this gives a reading of the temperature after the combustion reaction. So that will give the rise in temperatures. See, here is a gaseous fuel that is entering. So through the burner, when it is entering to the burner, it will burn. So this combustion heat, whatever is evolved here, heat that is generated will be absorbed by the water that is coming inside, then enter into the inner coil of the copper coil, and then goes to the water. So here is the temperature that is again reading. This is the initial temperature, T1 initial, T2 is the final temperature. So two thermometers are used. So T1 and T2, two thermometers are used. Assembly is covered with insulated to detach combustion chamber from atmosphere. So this is the insulation jacket or cover that is used so that it will avoid the loss of heat due to radiation. So for calculations, volume of gas that is burnt in T time is V per meter cubic. Then weight of cooling water circulated in time T is W kg, and initial temperature of incoming is T1. This is the T1, and the final temperature of outgoing water is T2. So the temperatures T1 and T2, the difference between these two temperatures will give rise in temperature. So rise of temperature in water is used for calculating the gross calorific value. So weight of water produced from steam condensation is mkg. So that will give the is used for the calculating, so that it gives the gross calorific value. So from the classification, if we see, fuels are classified into two different types, primary and secondary, natural or artificial it is also called. So in the primary fuels, solid, liquid and gaseous fuels. So if we see the examples of solid, wood or coal are the best example for the solid fuels. So coal is highly carbonaceous matter formed from vegetable matter buried in geomorphic changes. It means it is present in the environment. From the plant material, the coal is forming due to carbon that is present. So under pressure, by action of aerobic and anaerobic bacteria for longer time. When does it happen? Due to long reactions of aerobic and anaerobic reactions that takes place will give rise to coal. So for example, wood, if we take wood, that will form peat. Peat is loose matter that will be forming due to aerobic bacteria. Reacting with aerobic bacteria, it will give rise to peat, and due to anaerobic degradation or bacteria reaction, anaerobic for alkaline or acidic condition, both in alkaline or acidic condition will form coal, ultimate coal. So there are different stages and formation of coal. So lignite, then bituminous and anthracite. There are three forms of coals that are present, and that will be having different levels of carbon content and its calorific values. So if you see here in this picture, peat. This is the peat with whatever the plant material is present, the top layer of plant material. So that will be converting to lignite due to aerobic degradation. So aerobic or anaerobic degradation. Here anaerobic degradation takes place. So here is the aerobic degradation of wood that will takes place first and forms peat. Then anaerobic degradation gives rise to lignite, and then upon burial pressure. What is burial pressure? See, if we see this, here is the level of peat present. So once we go into the deeper into the soil, there is lignite that is present, and in more deeper into the soil, coal is forming. So due to heat, temperature, moisture, or the pressure and burial pressure that is present due to longer times, there is conversion of this matter into hard structures, that is nothing but coal that is forming. So conversion of peat to anthracite, there is increase in carbon content, carbon percentage, calorific value, density, luster is the appearance, hardness, black color intensity of that particular matter, and decrease in the moisture. Moisture will obviously decrease after some time when it is going deeper into the soil. Then volatile matter, then percentages of nitrogen, hydrogen, oxygen, sulfur and ash. This will be decreasing from formation of peat to anthracite coal. So peat generally contains 57% of carbon. So carbon percentage is 57%. The more the carbon percentage, the more will be the calorific value. So it should increase. The percentage of carbon should more increase so that we get good calorific value for our practical applications. So peat cannot be used for most of the applications because it has less carbon content. So only for the domestical purposes we use this peat material. Then 6% of hydrogen, 35% of oxygen, 3 to 6% of ash. So moving on to from peat to anthracite, the formation, during its formation, there is increase in the calorific value, fixed carbon or the carbon that is present. So it will increase. If we see this picture, it is loose material that is present. Peat is like a top layer of soil. Once it is becoming lignite or brown coal, it is becoming little harder and becomes a graphite in structure. So this is brown, fibrous in texture, then contains high percentage of water, and dried peat contains 15 to 25% moisture. So it has high level of moisture that is present. So that is why it is fibrous in nature and has a calorific value of 5400 calories per gram and low density in nature. So if we come to the uses, it is used as a domestic fuel and industrial fuel where low calorific value is required. So if whenever there are application with low calorific value, then we can go for this type of fuel. So used for soil conditioning. So we generally for the we use in the gardening purpose also, like conditioning the soil. Then used for steam rising, thermal insulation, packing, gas purification, sometimes for the power generation. So these are the different applications of peat, that is the first form of coal. Then lignite. So it has 65 to 70% carbon. So once it is forming a brown coal, the carbon percentage increased to 65 to 70%. Then 5% of hydrogen, 20% of oxygen, 10 to 15% of ash. So this is the composition of lignite or brown coal. So it is brownish black in color and more compact compared to peat, the first form of coal. Then it contains 45 to 50% volatile matter and burn long flame. So upon burning, it burns a long flame. So calorific value is 6000 to 6700 calories per gram. So there is an increase in the calorific value. So what happens? How does this happen? Due to heat and pressure. Under heat and pressure, this peat is converted into brown coal. So in general, the peat is really not called as a coal because it is loose and fibrous in nature. So the lignite, from lignite we call it as brown coal, then bituminous as soft coal, then anthracite as a hard coal. So this is how they keep increasing the calorific value. So that is the importance of the calorific value, which determines the nature or the capacity of that particular fuel in combustion. So after briquetting, it is used in domestic and industrial fuel and also used for producer gas, power generation, and on carbonization gives tar, that is used for laying roads. In roads also, wherever you are using tar roads, it is nothing but lignite that is used in laying the roads. Then comes the bituminous coal. So it has 70 to 90% carbon. So this bituminous coal has increased carbon content, and it is of three types. Subbituminous coal, non-caking coal, it is called non-caking coal, and composition is 70 to 75% of carbon and 35 to 40% of volatile matter. So volatile matter is also high. Then characters, it lies between lignite and bituminous coal. It is between the lignite and bituminous coal, and harder, denser than lignite, and black in color. So this, when it comes here, it is black color. If you see the lignite, it was brown colored, but it is turning to black due to increased content of carbon that is present. So the calorific value is 7,000 calories per gram. So it is used in domestic and industrial fuel. Then the bituminous coal, its composition is like 75 to 85% carbon, 20 to 30% volatile matter, black, dense and hard. It becomes harder, dense and black in color. Then cubical fracture structure, and calorific value is around 8,000 to 8,500 calories per gram. So if you see here, the calorific value is increasing as it becomes harder and harder in nature. The calorific value is increasing. So what are the applications? Domestic and industrial fuel, metallurgical coke, and power generation. So this can be used in further power generation, the carbon content and increasing the heat, latent heat also, as we go from peat to anthracite. Then the semi-bituminous coal lies between bituminous and anthracite, low volatile matter, has caking property. So the calorific value is 8,400 calories per gram with carbon percentage of 85%. So these are the three different types of bituminous coal. So the last one is the anthracite coal. So this is the highest containing carbon containing coal. So 92 to 98% of carbon with very low volatile matter. So there is no loss in using this coal. Ash is also very low and moisture is also very low. So these are low in levels, and it has lustrous black. So if we see this, it is shiny, lustrous and hard coal that is present. It burns with non-smoky short blue flame. So it has a short, the height of the flame will be shorter with blue flame. So that has higher intensity when compared to long flames. So that is why it is most widely preferred, and has the calorific value of 8,700 calories per gram. So this is very good, like as we go from peat to anthracite, the calorific value is increasing and also the hardness of the coal is increasing. So this is high cost because it has high calorific value. It will have more application, no smoky gas, no smoky flame. So obviously the cost will be expensive and used for special purposes, for high temperature heating, metallurgical fuels, and making electrodes. So graphite electrodes or carbon electrodes are nothing but made from carbon electrodes. These are nothing but made from anthracite coal. So these are the applications of anthracite coal. So in summary, if we see, this is the first stage. Wood has 50% of carbon with calorific value of 4,000 to 4,500 calories per gram, kilocalories per kg, and the domestic applications are like domestic fuel. So we, in the traditional method of cooking, we used to use wood as a fuel. So that is the most widely used in domestic fuel. So that has low calorific value which is sufficient for cooking. Then peat. The formation of peat will increase the percentage of carbon from 50 to 60%. So the calorific value is 4000 to 5400 kilocalories per kg and used if deficiency of high rank coal is prevailing. So this is used only in the case where lignite, bituminous and anthracite are not available. So whenever there is no non-availability of other higher rank of coal, then only we go for peat. Then lignite, it has 60 to 70% carbon with 6500 to 7000 kilocalories per kg of calorific value, used mostly for steam generation in thermal power plants. Then bituminous, 80 to 90% of carbon. So if we see here, there is very good increase in the carbon percentage from 50 to 80 from the formation of wood to bituminous coal. So this is having wide applications because it almost has 8000 to 8500 kilocalories per kg of calorific value. So it is most widely used and is coal gas, used in coal gas and metallurgical coal. So anthracite has the highest percentage of carbon, 90 to 98%, with a calorific value of 8650 to 8700 kilocalories per kg and is most widely used in the household and for steam generation or steam rising. So these are the different applications with the calorific values and percentages of carbon for different types of coals during its formation from peat to the anthracite type of coal. So in the next session, we will see the analysis of coal so that we will understand the chemical properties also. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.